Today we're going to be talking about graphing and evaluating polynomial functions. So you guys know the drill by now. As always, please start by trying the Ignite problem at the top of the page. Okay, final answer. You should have got C as your final answer. Now I'll talk about why that is. So first and foremost, when it comes to triangles, it probably helps to remember some of the properties from geometry. Probably one of the most important ones is that all angles in a triangle add up to 180 degrees. So if we take all three angles, angles B, A, and C, 35, 105, and X, and add them up, you should equal 180. In which case, all you have to do is solve. And if you solve that, you end up getting X to be 40. Now, the second one, this property is probably it's probably important, but not quite as important as all angles add up to 180. But angles that form a straight line are what we call supplementary angles. So if you add X and Y together, those should total up to be 180 degrees. So that's where our second equation comes from. If we take X plus Y, we get 180. And when we solve, we should get Y equals 140, excuse me. Now, final answer, it didn't say what is X and what is Y. It says what is the value of Y minus X. So that's all I did. 140, which is Y, minus X, which is 40. And total final answer, that's how we got C to be 100. All right. So obviously today we're not talking about triangles. We are talking about, though, different types of polynomials, some of the different kind of properties of those functions. First of which is something called the degree. Now, the degree of a polynomial is, in simplest terms, it's the highest combined exponent's power. So really, when we go through and look, we always look for the highest power. But I say combined because sometimes there might be multiple terms in a variable, or multiple variables in a specific term, in which case we would combine those exponents. But for the most part, we're not going to deal too much with that this year. But like, for example, let's say we had a problem where it was like 4x squared minus 7y cubed plus 10. If it was a problem like this, we would again look for the highest exponent's power. And the highest power in this problem is 3. And what that means is the degree on this polynomial, the degree is 3. I was just saying, like, what's the highest number? Because degree is something that we're going to use actually when it comes to graphing different sized polynomial functions. Because especially in unit 3, we're going to start to break away from the traditional quadratics and linear equations. We're going to get into some degree 3, degree 4, degree 5 polynomials, and we're going to go all about graphing those. So let's start off with, how do we tell if an expression is a polynomial or not? Because that's kind of the goal for today. We're only going to be graphing polynomial functions. So, and I forgot a really important word on this. I'm so sorry. But this says, how can we tell if an expression is a polynomial function or not? So specifically, there are 4 identifiers in determining something that's not a polynomial. Most functions out there are actually polynomial functions. But if any of these 4 things happen, then those polynomials are not actually, they're not a polynomial function. So first and foremost, if there is a fraction in the exponent, then that is not something that's a polynomial function. So if we had something as simple as if I had x to the 1/2, then because that fraction is in the exponent, then this would not be an exponent, or it would not be a polynomial function. Now, fractions, it doesn't necessarily mean you can't have fractions. If it was something like 1/2 x to the 4th, this is totally going to be a function because the exponent itself isn't a fractional exponent, which means it's okay. So be careful. It's not just that there's a fraction anywhere. It's that the exponent can't be a fraction. So the second case to tell if something is not a polynomial function is if there is a variable exponent or a variable in the denominator of a fraction. So for example, if we had like, the number, ooh, that didn't work, the number like 2 over x, boom, not a polynomial function because there is a variable in the denominator. Or we can make this equally as bad, is if I add to the top of the fraction 2 to the x. Times 2 to the x. Basically, anywhere if you see a variable in an exponent, it's also not considered a polynomial function. So reason number 3 to tell if something is not a polynomial function, and that is if there is a variable underneath the square root. So if you ever reach a point where you had like a square root of like a y cubed, something like this, boom, not a polynomial function. Now, we have to be careful because we can simplify things with square roots, right? We just talked about it in our last day. If I had like an x squared underneath, something like this would reduce to just x, in which case that actually is a polynomial function. So typically when we say a fraction or a variable underneath the fraction, it always has an odd exponent. Because that's something that we can't actually simplify moving forward. Ooh, that went crazy. That was awful. Sorry, guys. That's supposed to say add an odd exponent. And obviously, reason number 4 is if there are more than 2 variables in a term. So you can't have a 4xy somewhere in the problem. Or if I had like a 5zx plus 10. If there's a term that has 2 variable terms in it, or 2 variables in it, then boom, not a polynomial function. So let's actually start identifying some of these. Let's look at example number 1. So first it says, answer the following questions about the given polynomials. And these are things that are going to really help us when it comes to the actual graphing aspect. Now, we're obviously not graphing on this one, but first step is let's just simply tell, is it a polynomial or not? And the answer is absolutely not, because we are breaking rule number, which one is it? Hold on. Technically, this is rule number 2, because of the fact that it doesn't explicitly say this, but this kind of goes in line with rule number 2. Remember, when we have negative exponents, what that does is, remember, it moves those terms into the denominator of the fraction. So if you ever have a negative exponent, that's something that kind of also filters into rule number 2. So if you want to add that as a note to number 2, to say like that you can't have negative exponents, that's also part of it. But that's why this one, question number 1, it is not a polynomial function because we have that negative there. Now, this doesn't mean we can't answer some of the other important questions. The first is something called the leading coefficient. And this is the number in front of the term that has the degree. So first, let's start with degree. That's probably the most important question we can ask about this. Even though it's not a polynomial function, we can still answer this question. And it says, what is the degree? Well, the degree is the highest exponent in this problem. And the highest exponent on this one is 4. We have an x to the 4th. We have this one obviously doesn't count, but we have an x squared, and then we have a number. And in that case, the term that has the variable with the highest exponent, it just means that it's 4. Which means, is it even or odd? It just means that this is considered an even function because 4 is an even number. So if it just says, is it even or odd? It just means, is the degree even or odd, basically, okay? Now, because 4 is my degree, the leading coefficient is always the number that's in front of that term. So since x to the 4th, 4 is my degree, my leading coefficient is going to be -5. And last question I'm really going to ask you, and that is the number of possible zeros. This really is just a fancy question. It's the same as the degree. It just means that if you have a degree of 4, there's 4 possible places where you could cross the x-axis. Doesn't mean you always will, and we'll get into why that is a little bit later. But we just have to know that number of possible zeros. It just means we have 4 possible zeros. Okay? So what I want you guys to do, I want you guys to pause your video and give example 2 a shot. All right, final answers are up. First of all, first question was, is this a polynomial function? And yeah, basically if nothing weird is happening in an exponent and there's not a variable on the denominator of a fraction or a fraction anywhere in the exponents, then pretty much most of the time it's going to be a polynomial function. And this one it is because it doesn't break any of the rules from up above. Now, because in this case, the next question was leading coefficient, these two are kind of tied together, and you'll see with what we're going to do on the next page. But degree on this one, we said 5 because 5 is the highest exponent that we see in this problem, which means because it's 5, obviously it's odd, but also the leading coefficient is always the number that's in front of that term. So because 3 is in front, it just means the leading coefficient is 3. And last but not least, number of possible zeros. This is always the same as the degree, so we would say 5. All right, so now we're going to get into some of the different predictable pieces about polynomial functions. Now, obviously, something you're going to notice as we start kind of moving forward in Unit 3, and that is, we could have something as simple as a linear function, right? But polynomial functions are going to start, and they're going to be they look pretty weird, honestly, because there's a lot of curves. And that happens anytime you start increasing the degree of any polynomial function. So you could have any number of low points, high points, curves anywhere in there. It kind of depends on whatever function it is that you're working with. So one thing that we like to talk about once you get into some of no matter how crazy the graphs look, something that's pretty predictable about them is something called the end behavior. And it's exactly like it sounds. It's like we're going to predict what's happening to the ends of the graph. No matter how crazy the middle of the graph is, the ends are always predictable in where they're going to go. So to figure out the end behavior, we really look at two things. We base it on the degree, and we base it off of the leading coefficient. All right, those two things combined pretty much make up whatever the degree or the end behavior is going to be on our individual polynomial functions. So let's start off with the first case. So the first, when we say odd positive, odd negative, even positive, even negative, what those are talking about is the degree and then the leading coefficient. So if you have a polynomial with an odd degree, but a positive leading coefficient, let's just give an example. Let's say we'll stick with something pretty simple. Let's say it has an odd degree, and let's just start with probably one of the smallest, and that is a linear equation. So let's say we have a positive number in front and an odd degree, so either an x to the first or an x cubed. Let's stick with x to the first because that's the one that a lot of us know. If you were to graph this, I want you to really look at where the ends of the graph are going to go. Oops, sorry, guys. So let's say, for example, go away. Let's say we were going to graph a function that was just x squared, obviously. Nope, we're just going to graph just x. If you graph this is a function where we actually know where the ends of the graph are. We know that my ends of my graph basically are going to go up and to the right, and then down and to the left. So that piece of the graph, we're going to ignore the middle of it. What happens is, for every function that has an odd degree and a positive coefficient, the ends of the graph actually all follow that trend. The right end of the graph is always going to go up and to the right, and the left side of the graph is always going to go down and to the left. Whereas if you flip that, let's say it's still an odd degree, so we're still going to be dealing with an x, just an x, but let's say the leading coefficient is negative. Look at what happens when you try working with that piece. Let's say we graph the function negative x. Well, look at where your graph goes now. If you look at this graph, my graph actually switches. On the left side of my graph, we go up and to the left. On the right side, we go down and to the right. And that's pretty typical anytime we deal with a graph that has an odd degree and a negative coefficient. Ooh. Now the middle obviously isn't going to be the same. right? If I start making an x cubed, x to the 5th, x to the 7th, then those pieces are going to be different. But anytime we have an odd degree and negative coefficient, and I can actually show you, let's say we graph another function. Let's say we graph the function, I'm going to leave that one on there, but let's say we graph a negative x to the 5th, something a little bit more intense. Still a negative coefficient. Oh, no, not a negative coefficient. We want a negative coefficient, so negative x to the 5th. So still a negative leading coefficient, but an odd degree still, just a higher one. Look at where the ends of the graph go. Still, it looks more complicated, right? But the ends of my graph, it still goes up and to the left and down and to the right. So pretty predictable, at least the ends of the graph always are. If it's an even positive, we're gonna kind of go the same route. We're gonna say, well, what happens if we have an even degree? So let's say we have a squared and a positive leading coefficient. Well, we all know what an x squared graph looks like, right? That's my U-shaped graph. If it's positive, it just means those ends go up into the, both of them actually go up. Whereas if you keep that same degree, but have a negative leading coefficient, when we graphed quadratic functions, we called this a reflection because this graph, the U would actually go down. Now, we're not always going to graph x squared graphs, obviously, but the ends of the graph go the same place. It just means my ends of my graph are going to be going kind of down and away. So we can really kind of use that information and we can predict. Basically, you can kind of tell actually, if ever you have an odd degree, your ends of your graph are going kind of opposite directions, if that makes sense. And if it's an even degree, your ends of your graph kind of go in the same direction. They're either both going up or they're both going down. So something that I noticed just by looking at my first one, I don't actually know what the equation is, right? But my ends of my graph go different directions. It goes down and to the left and then up and to the right. So what that tells me is that this is going to be an odd degree. Now, because it goes up and to the right and down and to the left, that was our scenario where it was a positive leading coefficient. So that just tells me that whatever my leading coefficient was, it had to be positive. And more importantly, number of possible zeros, it just means that potentially it would be some sort of odd number. Obviously, you guys don't know, but this one right here, we can tell by looking at the graph. There is only one place where we cross the x-axis. So that just tells me number of possible zeros. It just means that there's one for right now. Now, let's do one more. So question number 4, it says, all right, let's start off with, is this even or odd? Now this one, because the ends of my graph are going the same direction, they're both going down, that tells me that this is an even function. Now, if they're both going down, usually for an even function, they both go up if it's a positive leading coefficient. So the only way we would get it to be going down is if it was a negative leading coefficient. Now, number of possible zeros for right now, we're just going to start with, well, how many are there? There's 1, 2, 3, 4, which makes sense because I'm supposed to have an even degree. All right, so number of possible zeros, we would say 4. So what I want you guys to do, I want you guys to pause your video and I want you guys to try examples 5 and 6. Answers for 5 and 6 are up. For number 5, you should have had an odd positive, just because ends of my graph go different directions, which means definitely going to be odd. And because I go up and to the right and down and to the left, that just tells me that that's the definition of a positive graph, of an odd positive graph. And possible zeros, there are 1, 2, 3 places where we cross the x-axis, so there are 3 possible zeros. Number 6, this one, you had, again, ends of your graph going different directions. So again, this one was also odd, but the ends of my graph switch. The ends of this graph go up and to the left and down and to the right, which just means that's opposite, so it would become negative. And there are 1, 2, 3, 4, 5 places where we actually cross the x-axis, so number of possible zeros is 5. Now, There is a notation that we are going to use when it comes to end behavior of graphs. And usually we just describe what's happening when we go to the extremes. When I go really far to the right and really far to the left, what's happening to my graph? Are the ends going up or down? So it's basically just what we talked about before. Like, for example, in example 3, we said this graph is going up and to the right and down and to the left. But we use a pretty specific notation for this. And we usually talk about it in, like I said, extremes. We're going to use infinity to describe this. Now, this first part says, and that's because there's always 2 ends to the graph. So let's start off with going to all the way to the left. So how it works is we basically start by looking at our graph and saying, okay, well, what's going to happen? If I go forever to the left, the largest number, the number that would represent the end, even though there is no end because there's infinity, right? But the furthest negative number that we can possibly reach, which is negative infinity. So we would say basically as x goes to negative infinity, what direction is y going? Is y going up or is it going down? Well, we already said this graph was going down and to the left. So if I'm going forever to the left and forever down, basically the extremes of this graph, we would say as x goes to negative infinity, f of x, or remember, that just means y goes to negative infinity. And it's basically just we're using infinity to describe the directions. So let's do the other way. As x goes forever to the right, or positive infinity, my infinity signs are awful, by the way, I'm so sorry. As x goes forever to the right, where does y go? Well, y goes forever up. So we would also say positive infinity. All right, so let's try number 4. Number 4 says, as x, let's go forever to the left. So as x goes to negative infinity, where is y going? Well, y is again going also down. This end of the graph is going down. So we would say y is going to negative infinity. The other one, as x goes to positive infinity, as x gets as large as possible, where is y going? Well, y is also going down. So it's also going to negative infinity. And that's how we describe end behavior. So again, what I want you guys to do right now, pause your video, and I want you guys to try examples 5 and 6. All right, answers are up. For this one, for question number 5, this one basically, these, and just so you guys also know, these really never change. X is always, we're going the 2 directions. We're always going to be going to negative infinity and then to positive infinity. It's the question of, well, where is y going? Because that's really what we want to know at the end of the day, right? So when it comes to graphing, so for this one, we would say as x goes to infinity, so if we go forever to the left, to negative infinity, where does y go? Well, the ends of my graph, it says we're going down. So we would say negative infinity. The other direction, as x goes to positive infinity, so as x gets forever larger, where's y going? Well, y is also getting forever larger. So it also goes to positive infinity. It's basically a fancy way for just saying where's your graph and where are the ends going. That's end behavior. That's the definition of end behavior. So for number 6, obviously as x goes to negative infinity, if I go forever to the left, the ends of my graph are going up. So we would say positive infinity. And as x gets forever larger, so to the right, where does y go? Well, y goes down in that case. So we would say y would be negative infinity. All right. So if you guys would like, I do have some you try now problems on the second page. If you want to give them a shot, go ahead and do so. I have the hiccups. Sorry, guys. But if you want to give these a shot, I will go over some of these in class. Thanks, guys. Have a great day.